To scale your AI architecture beyond a single server, you have to stop using direct synchronous communication. In an agentic system, a single user prompt might trigger an orchestration chain that needs to notify an auditing service, update a vector database, and trigger a long-running graph worker, all at the exact same time. If your frontend tries to talk to all of those services directly and just one of them is offline, your entire application crashes. To prevent this, we use message brokers. I want you to imagine your microservices architecture as a sprawling city. Instead of individual workers driving across town to deliver documents to each other, the city builds a centralized, hyper-automated global logistics hub. Services no longer talk to each other. They drop sealed packages into the hub and they drive away. The hub figures out who needs the package and handles the delivery. Let's break down exactly how this works. The logistics hub has two types of clients, publishers and subscribers. The publisher is the sender. Your FastAPI backend handles a user request, generates a message that says agent task started and drops it at the loading dock. The publisher does not know or care who processed this message. Its job is done. The subscriber or consumer is the recipient. These are your background services like a LangGraph Python worker. It sits there waiting, pulls the package when it arrives, and starts running its heavy AI loop. But not all logistics systems handle packages the same way. Depending on what your AI agent is doing, you choose one of three specific brokers. First, RabbitMQ. Think of this as the smart post office. You drop a letter in, a machine reads the label and drops it onto a specific conveyor belt leading to a specific worker. Once the worker reads it, the letter is shredded forever. This is perfect for task distribution. It ensures a task is handed to exactly one available worker. Second, we have Apache Kafka. Think of Kafka as a giant infinite digital ticker tape. When an event happens, it is stamped onto the tape. Multiple workers can read the tape at their own pace. But crucially, reading a message doesn't delete it. This is mandatory for audit trails. If an agent malfunctions, Kafka lets you rewind the tape to 9 hours ago and replay the exact sequence of events to debug the prompt. Third, Redis PubSub. This is the guy with the megaphone in the middle of a courtyard. It's a live broadcast. If you are standing there, you hear it. If you step away for 2 seconds, you miss it completely. There is no storage and no memory. We use this for real-time UI updates like streaming LLM tokens instantly to a WebSocket. When data moves through these brokers, it takes one of two shapes, a queue or a topic. A queue is point to point. It is a single line of message, first in, first out. One message goes to exactly one worker. If a worker A takes it, worker B never sees it. You use this when you want to execute a specific command. A topic is a broadcast channel. One message is cloned and sent to every single service that has subscribed. When an agent finishes a task, it hits the agent complete topic. The billing service reads it to charge the server. The email service reads it to notify them, and the vector database service reads it to index the data, all simultaneously from one single message. Now, what happens when things break? Language models fail constantly, APIs time out. When a subscriber pulls a message and processes it, it must send an acknowledgement, an ACK. back to the broker saying, I safely completed this and can delete it. But if the worker crashes due to an OpenAI rate limit, it sends a negative acknowledgement or NAK. If a message fails repeatedly, say 3 times, the broker assumes the package is toxic. Instead of letting it clog the main conveyor belt and crash your workers in an infinite loop, it routes it to a specialized quarantine zone called the dead letter queue. The DLQ is your safety net. It alerts your engineering team so you can inspect the exact payload, fix the prompt, and manually re-inject it without disrupting your live users. By using this architecture, you unlock 2 massive engineering superpowers. 1. Temporal decoupling. The publisher and the consumer do not need to be online at the same time. If your background workers go down for maintenance, your FastAPI server can still safely accept prompts from the users. The broker just stores them until the workers boot back up. 2. Backpressure management. If users dump 10,000 tasks into your system at 9 AM, your expensive GPU workers won't crash from out-of-memory errors. The broker holds the massive surge in a buffer, allowing your workers to pull tasks steadily at their maximum safe capacity. Senders, receivers, queues, topics, and the dead letter queue. Master the logistics hub and your AI backend will become virtually uncrashable. Till now, we explored the global logistics hub. We talked about publishers, subscribers, the dead letter queue, and the real-time megaphone. Now let's write the production grade Python code that brings this to life. We are going to use RabbitMQ to handle our heavy guaranteed tasks and Redis to handle our real-time streaming. Let's jump into the editor. Before any data moves, we have to design our shipping label and build our conveyor belts. First, the label. We use Pydantic to create an agent task. Every time a user asks our AI to do something, we package their ID and their prompt into this exact format. Next, we build the conveyor belts. Look at the setup_RabbitMQ function. Notice that before we create our main queue, we explicitly build the quarantine zone, the dead letter exchange. Then, when we create our main AI_tasks queue, we pass in special arguments, binding it directly to that quarantine zone. We are telling RabbitMQ, if a package goes toxic on this belt, automatically drop it into the dead letter queue. Now let's build the publisher. This is your FastAPI server. It is the front-end door of your logistics hub. When a user sends a prompt, notice the HTTP status code we use, 202 accepted. We are not waiting for the AI to finish. We take the user's prompt, generate a unique task ID, pack it into our Pydantic model, and drop it straight onto the RabbitMQ conveyor belt. Because we are using AI_Pika, this is fully asynchronous. The moment the package hits the belt, the FastAPI event loop is freed up instantly to handle the next user. While FastAPI is handling the traffic, our subscriber, the Python worker, is sitting in a completely separate server, pulling packages off the belt. Look at this line right here. Prefetch_count equal to 1. This is your backpressure management. Even if there are 10,000 tasks in the queue, this line guarantees the worker will only pull one task at a time, preventing out-of-memory crashes. Now look at how we process the message. We parse the JSON, run the heavy AI agent, and if it succeeds, we call message.ack. We acknowledge it and RabbitMQ deletes it. But what if the LLM hallucinates and the code crashes? Look at the value error exception. We catch it and we call message.nack requeue equal to false because we told RabbitMQ not to requeue it, and because we configured our quarantine zone earlier, RabbitMQ automatically routes this toxic task straight to the dead letter queue. Your worker stays alive and your bad data is safely isolated. So RabbitMQ is safely handling the heavy execution, but we still need to stream the live text back to the user's screen. For this, we don't use RabbitMQ, we use Megaphone, Redis PubSub. Inside our worker, every time the LLM generates a new word, we call redis.publish. We blast that token out into the ether on a specific channel tied to that task. Meanwhile, back in FastAPI, we have an open WebSocket connected to the user's browser. It is subscribed to that exact Redis channel. As soon as the token hits Redis, the WebSocket catches it and pushes it instantly to the screen. So, RabbitMQ for your guaranteed heavy workload and dead letter safety, Redis for your lightning fast real-time streaming. Combine them and you have a true enterprise grade AI backend. Hope this is useful. See you in the next video.